into constructing basically constructing the number system, making sure that the number system that we have rests on a good solid foundation, and that the assumptions that we put into our number system are all consistent and well-behaved and everything. There was a ton of effort that went into the logical structure of number systems. And so this first selection, and we're just going to sort of pick little bits and pieces out of this. I printed the whole thing for you, but we're just going to talk about little bits and pieces of the class. This first selection gives us some idea of how complicated that was. Okay, this is from Bertrand Russell, and he's one of the primary contributors to this whole foundations study, where he and Gottlob Frege, I'm not sure how to pronounce his name, and David Hilbert, and if you look at George Cantor and Peano, a whole bunch of big names who back in the late 1800s and early 1900s were trying to figure out where the foundation of mathematics was and what we need to take as a starting point and what the interpretation of all those different things were. Okay, and the first selection talks about a couple different schools of thought on fundamentals, okay? So, the fundamental thesis of the following pages, that mathematics and logic are identical, is one which I have never seen any reason to modify. The thesis was at first unpopular because logic is traditionally associated with philosophy and Aristotle, so that mathematicians felt it to be none of their business, and those who considered themselves logicians resented being asked to master a new and rather difficult mathematical technique. But such feelings would have had no lasting influence if they had been unable to find support in more serious reasons for doubt. These reasons are, broadly speaking, of two opposite kinds. First, that there are certain unsolved difficulties in mathematical logic, which make it appear less than certain than mathematics is believed to be. And secondly, if the logical basis of mathematics is accepted, it justifies or tends to justify much work, such as that of George Cantor, who is viewed with suspicion by many mathematicians on account of unsolved paradoxes, which it shares with logic. These two opposite lines of criticism are represented by the formalists, led by Hilbert, and the intuitionists, led by Brouwer. The formalist interpretation of mathematics is by no means new, but for our purposes we may ignore its older forms. As presented by Hilbert, for example, in the sphere of number, it consists in leaving the integers undefined, but asserting concerning them such axioms as shall make possible the deduction of the usual arithmetical propositions. Okay? So this is the key thing to focus on for that statement there. That is to say, we do not assign any meaning to our symbols 0, 1, 2, 3, 4, and so on, except that they are to have certain properties enumerated in the axioms. Okay. So what he's saying here is, the way Hilbert interprets the natural numbers is Hilbert says, okay, we have some things, and these things have absolutely no relation to reality. We're just going to label them. They're just going to be symbols. 0, 1, 2, 3, 4, 5. And we're going to take these things and define some algebraic properties that they have. So for example, 2 plus 2 is 4. 2 times 3 is 6. We can define algebra. We can define arithmetic. But we're just permuting symbols on some level. And they have absolutely no meaning. So for example, if you wanted to say that the first object was apple, and the second object was pear, and the third object was banana, then you could say pear plus pear equals banana. You just have a list of symbols, and you have algebra between them, but they don't necessarily have any relation to reality. You're just defining a logical system. Okay, so that's Hilbert's take on that. So let me just reread that real quick. We do not assign any meaning to our symbols 0, 1, 2, etc., except that they are to have certain properties enumerated in the axioms. These symbols are, therefore, to be regarded as variables. The later integers may be defined when 0 is given, but 0 is to be merely something having assigned characteristics. Accordingly, the symbols 0, 1, 2, 3, 4, and so on do not represent one definite series, but any progression whatsoever. That's what I was talking about earlier, that if you call it apple, pear, banana, and so on, that's just as good as if you call it 0, 1, 2, 3, and so on. You just have a list of things, and any progression you want, you can essentially relabel that 0, 1, 2, and 3 with any progression that you want, and it'll have the same algebra. Okay. So this is another key idea. The formalists have forgotten that numbers are needed not only for doing sums, but also for counting. Such propositions as there were 12 apostles, or London has 6 million inhabitants, cannot be interpreted in their system. For the symbol 0 may be taken to mean any finite integer without thereby making any of Hilbert's axioms false. Right? You could start the number system to have 0 represent 19, and then 1 would represent 20, and 2 would represent 21, and 3 would represent 22, and so on. So once you just use these as placeholders for a set of logical rules, they lose all meaning. And you can essentially apply those same rules to any list of sequences. So if you want to start at 19, 20, 21, 22, 23, you can just relabel them with 0, 1, 2, 3, and you get the same algebra, right? So that's what he's saying there, is that now all of a sudden London has 6 million inhabitants means nothing, because we could essentially start that by saying London has 0 inhabitants. And we've just, relabeled our system to start with 6 million starting at 0, right? So yes, and so he concludes that thus every number symbol becomes infinitely ambiguous. Okay. The formalists are like a watchmaker who is so absorbed in making his watches look pretty that he has forgotten their purpose of telling the time, and has therefore omitted to insert any works. Which is a pretty entertaining analogy there. Like, the watchmaker is so engrossed in making a nice, pretty watch, gold highlights and everything, that he's like, oh yeah, I forgot it has to tell time, right? Another difficulty in the formalist position is regards to existence. Hilbert assumes that if a set of axioms does not lead to a contradiction, there must be some set of objects which satisfies the axioms. For him, existence, as usually understood, is an unnecessary metaphysical concept, which should be replaced by the precise concept of non-contradiction. Here again, he has forgotten that arithmetic has practical uses. Have you ever thought that there might be a war within mathematics? You're basically like witnessing the war here of the formalists and the intuitionists. Okay. The intuitionist theory, represented first by Brouwer and later by Weil, is a serious matter. There is a philosophy associated with the theory, which, for our purposes, we may ignore. It is only its bearing on logic and mathematics that concerns us. The essential point here is the refusal to regard a proposition as either true or false unless some method exists of deciding the alternative. Brouwer denies the law of the excluded middle, for which no such, where no such method exists. There's a certain method of proof called contradiction, proof by contradiction, and some mathematicians believe it's bad style to accept proof by contradiction because, well, we can't really get into it here, but look that up on Wikipedia if you want to get into it, the law of excluded middle. And yeah, we're not really going to get into that in this class, so let's go move on. Let me see. Okay, yeah, let's go just finish up with this last little bit here. So associated with the intuitionist theory is a doctrine called finitism, which calls into question propositions involving infinite collections or infinite series on the ground that such propositions are unverifiable. That, we can't handle infinity in the intuitionist model. If taken seriously, this has consequences even more destructive than those that are recognized by its advocates. Men, for example, though they form a finite class, are practically and empirically just as impossible to enumerate as if their numbers were infinite. If the finitist principle is admitted, we must not make any general statement, such as all men are mortal, about a collection defined by its properties, not by actual mention of all its members. Right? You can't say, just by a broad brush, that all men are mortal. You have to check every individual man in the world and say, are you mortal? And that's the only way to verify it, if you check it. And you can't just paint with a broad brush and say, all men are mortal. Okay. This would make a clean sweep of all science and of all mathematics, not only of the parts which the intuitionists consider questionable. Disastrous consequences, however, cannot be regarded as proving that a doctrine is false, and the finitist doctrine, if it is to be disproved, can only be met by a complete theory of knowledge. I do not believe it to be true, but I think no short and easy refutation of it is possible. Anyway, so that gives you a flavor for the types of questions that we're going to be they're going to be going on in the background as we proceed. But as you can see, very, very interesting philosophical ideas. Oh, good news, by the way. Since we're going to be working out of this book for about a month, you don't need to bring those big old hunky textbooks. Yeah. I like that as much as you guys do. So let's move on to the Landau text. So this guy, Edmund Landau, I don't really know much about him as a mathematician, but he wrote this text. It's kind of an interesting story because it's as he says here, my daughters have been studying chemistry at the university for several semesters already, and they think that they have learned the differential and integral calculus in college, yet they still don't know why x times y is the same as y times x. And I just think that's really fascinating because everyone knows that it's true, but if I ask why is it true, very few people will be able to answer, right? So we're going to get to see why x times y is the same as y times x. We're going to see where algebra comes from. Okay. Let's go ahead and flip to page 1. And we're not really moving into the material just yet. We're going to just take a look at one quick little thing in the material, and then we're going to go back, okay? So we're going to start here. We're going to say a set of objects is called natural numbers, possessing the axioms to be listed below, okay? So we're going to talk about natural numbers, right? And we're thinking, oh, cool, that means 1, 2, 3, 4, 5, and so on, right? And the answer is no. That's actually not what it means. What we're going to do is we're going to say, take a set and assume that it has the number 1 in it. But for now, that's all that we're going to assume. You have a set and it has the number 1. So we're not even assuming that we have the number 2 or the number 329. Those numbers, we threw them out the window, okay? And we're just going to start by saying, okay, assume that there's a set. It has this thing called a 1. And then we'll build up some other stuff from there, okay? So with that in mind, that we're throwing out all the natural numbers and we're starting from scratch, let's flip to the introduction. I love the first sentence. Please don't read the preface for the teacher. So naturally, I made sure to print that out for you guys so that you can go read it. It's not going to make much sense, but once you see a sentence like that, it's like the first thing you're going to do, go read the preface for your teacher, right? So I printed that out for you. Make sure you at least glance over it, and you'll find pretty quickly why he told you not to read it. This is a key idea here. I will ask of you only the ability to read English and to think logically. No high school mathematics, and certainly no advanced mathematics. Okay. Now, to prevent arguments, a number, no number, two cases, all objects of a given totality are completely unambiguous phrases. Theorem 1, Theorem 2, Theorem 3, Theorem 301. Also, line numbers like line 1, line 2 are simply labels for distinguishing the various theorems, axioms, definitions, and so on. And we don't want to call them theorem light blue, theorem dark blue, and so on. What the hell is he saying? He's saying, just keep in mind, we're going to throw out the natural numbers entirely, and we're going to start from scratch. So does it even make sense to say theorem 2?
So you're just renaming whatever, and it could be anything, you're just giving it another name.
Yeah, exactly, right. So that's what he's saying, is that we're just using them as labels. These are not numbers anymore. They're labels, because we're throwing numbers out the window for a while until we rebuild them properly, okay? So that's all that he's saying in this first case. It's like, oh, how can you have a theorem 2 if there is no 2? Okay, very cute, right? So, let's read through this paragraph here. We're only going to go through chapter 1 in this text. Okay. I developed corresponding material in each of the chapters in turn. In chapter 1, we do it for the natural numbers. In chapter 2, for the positive fractions and positive rationals. In chapter 3, for the positive, rational, and irrationals. And in chapter 4, for the real numbers, both positive, negative, and 0. And then in chapter 5, he does it all for the complex numbers. So, for example, he's going to define addition. So in chapter 1, he defines addition for the naturals. In chapter 2, he defines addition for the rational numbers. In chapter 3, he defines it for the irrationals. In chapter 4, he does it for addition of positive and negative. And he defines addition of complex numbers in chapter 5. You may have gotten all that, but anyway. So he then goes on to say, please forget what you learned in school. You haven't learned it. So starting from scratch. But he says, please keep in mind all the corresponding parts of your schoolwork. You haven't actually forgotten them. We're going to be building up all of the properties of arithmetic. But he says, we're not going to do arithmetic. We're just going to build up the properties of arithmetic. He says the multiplication table is not found in this book, not even the theorem that 2 times 2 is 4. But I would recommend as an exercise that you make the following definitions. Define 2 to be 1 plus 1. Define 4 to be 1 plus 1 plus 1 plus 1. And then prove the theorem yourself. And then that one last little comment. My daughters have been studying chemistry at the university for several semesters already. I think they've learned differential and integral calculus, but they still don't even know why the commuter law is true. So any questions on the introduction? Just out of boredom last night, I flipped through the text to look and see if I found the number 2 anywhere. And in the whole text, once he starts the actual text, he does not use the number 2 anywhere. He did at one point write this. He did write 1 plus 1. But he didn't label it 2. Okay. So a couple of comments on the structure of what we're going to cover here. This is the difficulty level. So let's let A be a set of objects. We're not going to give it a name just yet. We're just going to call it A. And elements in A are going to be called numbers. Okay, then we'll write x equals y if x and y are the same number. We'll write x not equal to y if x and y are different. Let's take a look at a couple little points of interest here. First of all, x is always equal to x, because x is the same number as x. And if x is the same number as y, then y is the same number as x. And we also have if x equals y equals z, then we certainly know that x equals z as well. It's just based on the definition of sameness. X is the same as y is the same as z, so x has to be the same as z. Okay, so just a couple little baseline rules about equality. So far, we haven't done anything, right? Because the set A that we've defined, technically we don't even know if there's anything in it, right? These rules about equality, they say, if you have something, first of all, then these rules are going to apply. But if we're just saying let A be a set, we don't even know if there's anything in it, right? It could be the empty set. So, axiom 1, right? Axiom is just a basic assumption that you're going to make. Is that, first of all, there exists a number in A, and we're going to call it, we're going to give it the label 1. If you take a look in your text, this is how extreme this guy is. He's like, all right, first of all, we're going to assume that we have something, and we're going to call it 1. And this is how you pronounce it. You say 1.
Well, that's easy.
So we'll note, first of all, that we now know that our set A is not the empty set. Okay. Axiom 2. Assumption 2, right? An axiom is just a baseline assumption that you're going to use to get started. Axiom 2 says we have this thing called 1. So we know that we have something in our set, right? Now, pick up any object in your set. You can find something called the successor to that object. And there's only one, right? X can't have two different successors. X can only have one successor. Okay. So I've mentioned already that we're starting from scratch and we're assuming that we don't know anything about the natural numbers. But just for clarity, I think that let's pretend like we actually do know that. 1 has a successor. What is it?
2.
Exactly. The successor to 1 is a number that we're used to calling 2. 2 has a successor as well. What is it? 3. Okay. So that's all that you want to keep in mind when you see successor. It's just the next natural number. Okay. But we're not going to call it 2 or 3 or 4 or 5. We're just going to call it the successor to x. And we have to know that when we have 7 successors, that's the number 8.
So that one, that dash is called successor, that's what.
Yep. So that's sort of what we want to think of. We want to think like this. But we're not allowed to. Okay, because let's take a look at an example that shows that we do not yet have natural numbers. And here's the system. Let's suppose that 1 is an A, because axiom 1 says we're going to have at least 1 there. Okay. So that's true by axiom 1. Then let's go and label the successor to 1. Let's let that be 1. Then what's the successor to the successor of 1? Well,
3.
it's the successor of 1, which is also 1, right? And what's the successor to the successor to the successor?
Still 1.
Still 1, right? So let's review the axioms. We've got axiom 1 says, assume that you've got an item that you can work with. Okay, we're going to call it 1, right? Does this satisfy that first axiom? Yes. Okay, so we're satisfied axiom 1. Now, we need to define a successor, right? And this has the property that we're going to define the successor to 1 to be itself. Meaning there's only one successor to 1. It's called 1, right? So is axiom 2 satisfied? Yes. We've got a successor, right? I guess technically we should say set A equal to set 1. Okay. So let's set A equal to set 1. Then clearly 1 is an A, so the first axiom is satisfied. Define the successor relation to be the successor of 1 is always 1. Then clearly we can take as many successors as we want. We always land back in the same set A. And so that guarantees that axiom 2 is also satisfied. So what do you think? Does that look like the set of natural numbers?
No.
No. So we clearly need some more axioms to make this behave the way we want it to behave.
That's where you get plus sign.
That'll come later. Yeah. All right. Before we go on to the next axiom, I'm going to prove what I'm calling theorem 0. And this is not in the book. Because this is a fact that comes up quite a bit. And Landau just assumes that it's common sense. But I want to actually work through it. Okay? So theorem 0 says, if x equals y, then the successor to x equals the successor of y. So, in this proof, we're going to let x equal y. Then you'll recall, by definition, that means x is the same as y. Right, that's the definition of equals. X and y are the same. And by axiom 2, we know that we may form the successor to x and the successor to y. Axiom 2 guarantees that we're allowed to even construct this. Right, because if you think about it, you say, if you don't have axiom 2, you say, suppose that x equals y, then do the successors equal each other? Well, you need axiom 2 just to say that you can even construct them, right? Because what does it say? It says, there is, meaning there exists a successor to each element of A. So axiom 2 is required to make sure that you can even construct those. Then clearly, that little apostrophe there is called a prime. Okay. Clearly, x prime is the successor to x. And also, since x and y are the same, we know that y prime is also a successor to x. X and y are the same thing, and taking the successor to y is really taking the successor to x. Okay? And notice in axiom 2, we have this uniqueness here, that whenever you have a successor, it's unique. There's exactly one successor to every item, right? And so, by the uniqueness guaranteed in axiom 2, we have that x prime is the same as y prime. X prime is a successor to x, y prime is a successor to x. Therefore, by uniqueness, they have to be the same.
So by uniqueness, they're the same? But wouldn't that be like a contradiction? Because if it's something unique,
It's kind of like saying, I am Brian Palmer and I am Brian Palmer. It's like saying, okay, it's like saying Barack Obama is commander-in-chief and Barack Obama is the chief executive. By uniqueness, if there's only one Barack Obama, then chief executive and president of the United States have to be the same. Yeah. So, what we've done so far is something that we talked about on day 1 of this class. We can think back to day 1. We talked about how math is essentially, you've got definitions, and then you have axioms, which are, properties of the things that you've defined, right? Axiom 1, axiom 2. And based on the definitions and based on your axioms, you then start to construct logical consequences, right? So we've got our first logical consequence that we call theorem 0, which says, okay, we have a definition. We took this thing called 1. Or no, I guess we didn't take a thing called 1. We took a thing called a number. And we took a thing called a successor, right? So there's another definition we use. And we took this thing called equality. So there's another definition that we used. And we took that together with some properties that we assumed in axiom 2. And based on those definitions and based on that axiom 2, we've reached a conclusion that has to always hold. That if two numbers are equal, the successors are also going to be equal. Okay. So I guess, let me see. I guess we also used axiom 1 in the sense that we took numbers that we know have to be there. Axiom 1 says we have existence. of these things called numbers. In particular, there's at least this one that we're going to call 1. Okay? So yeah, we used some definitions, we used both axioms, and we used that to derive a conclusion that now always holds forevermore in this logical system. If you have x equal to y, then the successors have to also be equal. All right, so let's take a little break. Guess we meet back at, going back to what we talked about before. So far, we've only got 2 different axioms, right? Axiom 1, axiom 2, and we found that if your set is just the set containing 1, together with the successor operation that one successor is equal to 1, that's perfectly valid under this system, right? But does that mimic the natural numbers in any way? Not at all, right? So clearly, we need to expand our axiomatic system to include more requirements, because with these 2 requirements, anything goes really. You can have all kinds of weird systems, and it doesn't behave like natural numbers, right? So you might ask, why don't we just toss in a requirement that the successor to x cannot be x? Wouldn't that fix our situation? And what do you think? Does that sort of solve the problem that we run into?
Because y is equal to x2.
No, it doesn't have anything to do with that. I'd be surprised if anyone is able to figure out what I'm looking for when I say this. But it turns out this is not enough. Just saying, make sure the successor of x is never equal to itself. That's not enough to give us a natural number still. It means something
Is
more.
it because x already exists and you can't just, there's already an x?
I would need to hear a little more.
Well, isn't the successor what comes after the x?
Well, the thing about this system is that it doesn't always have to be quote unquote after, right?
Oh.
If you have the successor just equal to the original number, you've satisfied the requirement that you have a successor, right? And it gives us this nonsense where you just have a 1-unit set, right? So you could say, why don't you just throw in that requirement? Is that enough to give us the natural numbers? And the answer is no, it's not. Because if you think back to something like collaborate, okay? 12, 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the successor to 1? 2. What's the successor to 2? 3. You go all the way around, what's the successor to 11?
12.
12. And what's the successor to 12?
1.
So this doesn't actually give it to us. It gives us new stuff, right? That you have to have something different from 1. One successor can't be 1 anymore. But that doesn't mean that you aren't. That doesn't mean that you have the natural numbers. You could have this cyclic behavior here, where it's like we still don't have the natural numbers, even if you throw this in as an axiom. Okay. So that's not strong enough to give us natural numbers. We're actually going to include a different axiom that is surprisingly far-reaching. It seems very simple, but it's surprisingly far-reaching. And it gets us very close to having natural numbers, but still not there yet. Okay? So axiom 3 says x successor can never be 1. No matter what x is, the successor to x can never be 1. And so that fixes this problem, right? That eliminates this cyclic behavior where if you loop back around, this is not allowed anymore, because once we get to 12, guess what? All of a sudden, 1 had a predecessor, right?
You're just repeating it over and over.
Yeah,
It's like a dog chasing its tail, memorization.
exactly. And so this throws that out. It says nothing can can never succeed to 1. 1 cannot have a predecessor. So that says you can't loop around like that, because then 1 would have a predecessor. Okay? So first of all, the first thing you'll note is that this throws out cyclic behavior. And you may not notice this at first, but it also guarantees that there's more than one item in your set. Because think back to this example. If A is the set 1, and you just define the successor to be 1, it satisfies the first axioms, but you'll notice that you just have a one-item set, right? Once you throw in this next axiom, we know that if you take the successor to 1, it's not going to be 1, because this requires that every successor can't be 1. So this also guarantees that there's more than one item in the set. And another very important point to make is that it also guarantees that 1 behaves the way we want it to. We want to think of 1 as our quote-unquote starting point, right? And that's what this axiom guarantees for us. It says there's no predecessor to 1. So 1, just like we always wanted it to be, really is our starting point. Okay? So this axiom guarantees that 1 really is what we want it to be. A starting point. So it looks like a pretty simple axiom, right? 1 cannot have a predecessor, but it has all these really interesting consequences that you don't have if you just have the first 2 axioms. Okay. So now, do we have natural numbers?
Not yet.
Not yet, still not? Are you sure? We know we have 1. And we know we have something different from 1, right? 1 successor cannot equal 1. So we know we've got at least 2 numbers. What comes next? The successor to the successor of 1. Axiom 3 guarantees that these 2 are different, right? They're different by axiom 3. What about these 2? Is there any difference between the successor to the successor of 1 versus just the successor of 1? Are those different? Not necessarily. Good, I see people shaking their head. Not necessarily different. We know by axiom 3 those have to be different, but we don't know anything about these. These, for all we know, may be the same. The only thing axiom 3 says is that if you take the successor to 1, you know it's not 1. And so, let's take a look at this example again. Let's define define 1 to be 1. And let's define the number 2 to be the successor of 1. Let's define 3 to be the successor of 2. And let's define 3 to also be the successor of 3. So we're defining all this stuff. And how do you count in this number system?
1, 2, 3, 3.
Yeah. In this number system, you count 1, 2, 3, 3, 3, 3, 3, 3, because the successor of 3 is itself. And so once you reach 3, you just keep counting 3 over and over, right? The successor to 3 is 3. So the successor to the successor of 3 is 3. And so you end up just counting 1, 2, 3, 3, 3, 3, 3. But you'll notice that, first of all, axiom 1, do we have something called 1?
Yes.
Yes. So axiom 1 is satisfied. Axiom 2, which says, is there a successor? For every element, do you have another element called a successor? And the answer is yes. So that's satisfied. In axiom 3, does 1 have a predecessor?
No.
No. We want it to not have a predecessor, right? Nothing comes before 1, and that's exactly what's happening here. Nothing has a property that when you take a successor, you get 1. So axiom 3 is satisfied. This still doesn't look like natural numbers. Getting ready to give up, just go home. We're never going to get there. Let's introduce another axiom.
Let's just start fresh.
So axiom 4. Axiom 4 says, if the successors are equal, then the predecessors also have to be equal. And so what do you think? Do we have natural numbers? Let's take a look at that last example. We have 1. How should I write this? I guess I'll just write kind of the way we had it. The successor to 1, which we called 2. The successor to 2, which we called 3. And the successor to 3, which we called 3. So does this satisfy axiom 4?
Predecessors, they're
Keep looking. 2 and 3, the successor to 2 and the successor to 3, right? So here we have a successor, 2 successor, that's a successor, right? And what's it equal? It's equal to 3. Now here we also have a successor, that's 3 successor. And what is that equal to? 3. And so what do we have? We have that 2 successor is equal to 3 successor, but this one had a predecessor of 3, this one had a predecessor of 2. And so we see those are not the same. We therefore have that axiom 4 fails. We have two successors that are the same, but the predecessors are not the same.
So axiom 4 just doesn't work.
In this system, axiom 4 fails.